Okay, hi everyone. Great to see you all here. I'm waiting for the slides. Okay, let's see. And now, how did I put this in full screen? All right, here we go. Yeah, welcome to our talk. I'm Sam, and together with Amy, we will talk about JavaScript engine security in 2022. It's going to be more of a high-level talk. So we're not going to do a deep dive into any specific bug. Instead, it's more of an overview talk. We do link to lots of resources for those interested in more details. And we'll also keep it light on JavaScript language internals. Although we do need a little bit of that, so we'll start with that. For JavaScript, really the only thing you need to know for this talk is it's a very dynamic language. And so, for example, that means it has dynamic typing. So here you have a variable v. Here it's a number, but then nothing prevents you from setting it to a string, right? And then this variable slot on the stack, it's then a pointer to a string somewhere, or you can set it to an object, and then it points to this, whatever this is. And so all of this can change, right? And so next we'll look at how objects look like a bit in memory. Again, this is kind of a high-level concept. This is roughly how all the major engines do it these days. And so similar code snippet, right? You have you're creating an object with two properties, and so what you end up with is the object in memory, which has a pointer to a type or a hidden class. I think it's called hidden class just because it's similar to a class in C++ or Java, except it's hidden to the programmer. And so now this hidden class, this contains the information where those properties live, right? And so in this case, it says A and B are both inline properties, and so they are stored directly in that object. And here, if we were to load property A to print it, for example, what the engine does, it goes to this object, it goes to the type, to the hidden class, asks, hey, where is property A stored? That tells it it's inline in the object, and so then it goes and fetches it. Now, one of the main reasons for doing this separation of object and type is that you can share those type objects. So if we were to create another similar looking object like this here with, again, A and B properties, it can point to the same hidden class in memory. And so you save some memory, for example. But again, all of this is dynamic. All of this can change. And so here, for example, we can add another property to this O2 object, right? And so then what happens? Well, we can no longer point to the first hidden class because it doesn't have C, so we need to create a new one. The other problem we might have in this case is that we don't have any more space in the object itself, and so we need to allocate some kind of out-of-line property storage, right? Like some property array maybe, and then that again has those slots, and the hidden class says C is stored out of line, slot 0. And we could do even more shenanigans, like we could delete properties that exist, in which case, again, we need a new hidden class that now only has B and C, and the slot 0 is in some deleted state, right? So again, main takeaway, all of this can change. It's a very hostile environment, I would say, and we'll see how this breaks things later. So here's a small kind of summary of typical JS engine components. We'll do a quick walk through how they work together to run your JavaScript code. So JavaScript code comes in here, for example, from the web browser, where it fetches it from the network. First thing it does, it goes into the bytecode compiler, and so that compiles it to engine-specific bytecode. So each of the major engines, they have their own bytecode format that they optimize for their respective interpreter, for example. So that's the next thing that happens. The bytecode gets executed or interpreted by an interpreter, and while it does that, it interacts with what we're just calling the runtime here, which is basically the set of like all the constructors you have available, all the built-in objects, built-in methods and so on, like your whole environment. And while that runs, it creates a runtime state. Like, for example, it sets up objects, as we've seen before, links them together. It creates kind of a graph of things referencing each other. Now, eventually, if this bytecode runs for a long time, it gets hot, what they call it. And at this point, the engine decides, well, maybe it's a good time now to optimize this code further so your web page runs faster. Puts that bytecode, feeds that into the JIT compiler, which then optimizes the code and produces machine code. And that should hopefully be very fast. And now everything is nice and smooth. But otherwise, it behaves the same as the bytecode, right? It interacts with the runtime, does its thing, in a more performant way. Now, eventually, JavaScript is a garbage collected language, so it means the programmer doesn't have to manually alloc in free things. Instead, there's a garbage collector which takes care of figuring out when memory is no longer referenced. Here in this example, like there's some node, here's some object that isn't referenced by anyone, so the collector comes in, does kind of a graph walk, figures out this object, no one is using it, and it frees it. And then finally, there's also WebAssembly, which is integrated in the JavaScript engines. It's basically a bytecode format for the web. If you want, you could take C++ code, compile it to WebAssembly, run it in your browser. And this has a slightly different pipeline, but it's mostly really just the front-end part that's different. So there's a different compiler that takes the WASM bytecode format and converts it either again to some other bytecode or directly to JIT code. In this case, this works for WASM. It doesn't really work for JS, and we'll see why in a second. Okay, so with this short introduction, we're going to zoom into one of the most complex parts, which is the JIT compiler. It's going to be up next, and we will start with kind of a simple example for how JITting of JavaScript works. So here's some, I just made up this code here. It's like a kind of a bitmap thing of 8-bit integers, and there's a function set, and you give it a point and a value, and it's going to set the bitmap at that point to the provided value, right? It does a bit of sanity checking. It tries to make sure that X and Y are within the range, but yeah. So really the first problem, if you just wanted to like convert this to machine code, the big problem you have is you don't actually know what P is, like what the type of P is. I mean, if you look at this, you would guess it's probably an object with property X and Y that are probably numbers, but there's nothing that guarantees that. Like we could run this with a string, and in that case, it would do weird things. And so this can actually be JITted just like that. So what has to happen first is the code has to run a couple of times in the interpreter. And while it runs there, the engine gathers type feedback. So it remembers, okay, this function has been called with this type before and only this type. And so sometimes this is called training, so we need some kind of for loop that just calls this. And now we can start with some JITting. How I'm going to do this is on the left side, it's highlighted the line that's being JITted, if you want. On the right, there's some JIT intermediate language pseudocode for the highlighted snippet. And so in this case, the first thing that happens is bytecode parsing. The JIT engine takes in the bytecode and turns it into some high-ish level JIT intermediate language. In this case, it still has pretty high level operations. It's just like load property, do a compare, load property, do a compare. What's going to happen next is two things. The first part is speculation, which is exactly where this feedback from past executions comes in. And so the engine sees, okay, P, so far P has always been this like object type 1 with property X and Y and so on. And so it speculates that this will be the same in the future. And it just puts in a type check. And if that check fails, then the runtime will actually just go back to the interpreter, and this code will not continue. And then it also, by that point, it knows the type, so it can convert this high-level load property operation to a low-level load field +8 thing. So that's called lowering. Now, if you look at this code, you realize, well, it's kind of redundant, right? Like we're doing this type check twice, we're doing the load twice, there's nothing in between that could really mess up anything. And so here's the first round of optimization. The compiler figures out this is redundant and it drops the second pair of these operations. Let's look at this line down here, where it stores the value into the uint8 array. And again, at first, this is going to look pretty high level. It's loading the global value w, doing a generic multiplication, a generic addition, loading the global BMP value, and doing a generic store element. Same kind of similar thing here. We do lowering, and in this case, we also do constant folding. We know that w and BMP are constants. They can change. We don't need to load them. We know that x and y are integers. We can do a specific integer multiplication. And we also turn the generic store element, we turn it into a check bounce and like just a write into an array operation. So let's do another optimization here. This one is called range analysis and or bounce check elimination. If you look at the if condition, you will see, and the compiler will conclude, that at the highlighted line, x and y must be integers in this range 0 through 64. And so if you know that, then you can figure out what the possible range of values is after the multiplication, this here, and then you can also figure out what it is after the addition. And then you see, well, this bounce check is really not necessary. The bounce check just checks if it's between 0 and 4096, but we already know that. So let's get rid of this bounce check. Because it's very expensive, of course. We don't want to do bounce checking. And so yeah, we can get rid of that. And here's the kind of final JIT code for this example. It's really just those few low-level operations. And those can more or less just be lowered to one or a couple of machine code instructions. Like the load fields, it's just going to be like one move or LDR, the multiplication and addition, and so on. Cool. So this is a short summary of what we've seen. Like, how does a JIT work on a high level? It starts from unoptimized bytecode. It does speculation based on feedback. Then it does a number of rounds of lowering to the next lower level language, optimize on that, and then at the end you have machine code. All right. So let's look at a hypothetical example for a bug. Another JS snippet. It's just a function that takes in supposedly an array, a callback function and a value, and it calls findIndex. FindIndex will go through the array, call the callback for each value, and once the callback returns true, it returns the index for which it returns true. And then this function takes that index and sets the value to the provided one. So now, if you did kind of a similar thing as we did before, you would maybe end up with this code where it does a type check that A is an array, calls into the runtime, does a bounce check, and stores into the array. Now, you might be tempted to try some range analysis here. And you might conclude, well, find index, I mean, certainly this is going to give me an index back. So the value I get, or the range for I, is going to be between 0 and whatever the length of the array is. And then you're very happy to remove this bounce check and save some executions at runtime. But no, this doesn't quite work. Because, of course, if the value is never found, then find index, in this case, it returns -1. And so this would give you an out of bounds read or write, write in this case, in front of the array. Yeah, so that doesn't work. Of course, this is a very simple example, but I think it kind of highlights the point. So now you might be tempted to say, okay, let me fix up my range analysis. Really, it's between -1 and the length of the array. And so then maybe I can kind of simplify this bounce check. I just need to make sure it's bigger than 0. No, it's not negative, larger or equal to 0. But again, this doesn't quite work. And now the problem is callback trickery. What you can do is in this callback that you give to find index, you could resize the array. You could just set its length to 0. The backing store would get reallocated or so, and then again you get an out of bounds access into this array. Yeah. So this is what I meant before when I said it's a pretty hostile environment. There's so many things that can change all the time. So you need to be very careful. Okay, so enough with hypothetical bugs. Let's look at some real bugs. So this picture, and no worries, we're going to go through it step by step. No worries. This lists like kind of a lot of the JIT bugs we've seen in the last few years. They are all linked there. The kind of barrier for inclusion was there had to be some decent write-up of the bug. So all of these are really great resources. And so yeah, let's build this up step by step. So we start from these red bubbles. Those are kind of the fundamental memory in safeties, if you want, right? You have spatial memory safety means if you have an array when you access is out of bounds, then you're violating that. Type safety is violated by a type confusion. You think your object is of type X, but really it's of type Y, so that's your type confusion. And temporal memory safety, well, if you're using an object after it has been freed, then you have a temporal memory safety violation. And so the way to read this is there are optimizations and analysis passes. They have different colors. And an arrow here just means one breaks the other, okay? And so bounce check elimination, I think that's pretty obvious, and it's what we've just seen. If bounce check elimination goes wrong, that breaks spatial memory safety. Now you have removed a bounce check that you shouldn't have removed. That gives you out of bounds access. And there were actually, there was at least one bug some time ago, 2017, directly in the bounce check elimination itself, not even in the analysis. I think it was something where they just forgot to check for negative numbers. Like they had all the range information, but they didn't actually check if, they just checked was it below the bounds, but not was it bigger than 0. And so then they removed it. But then starting 2017 and 2018, a lot of bugs came up in the range analysis itself. And that is a much more complex thing. That is like you need to model every operation in your JIT IR and compute the output range. And so lots of things go wrong. They're kind of similar to the example we've seen. So yeah. So look at another kind of another group of optimizations here, which is type check elimination. Also similar to what we've seen. So this might be a case where you have two type checks for the same type, and then the engine decides it doesn't actually need one of them and drops it. The big issue that can happen here is your engine thinks it can remove this type check, but actually in between the type changed. And so in that case, the second type check would have been necessary, but it was removed, so you get a type confusion. And those, again, they were kind of early JIT bugs, I would say, 2018, 2019-ish. There was one 2020, but yeah. Then we have this optimization here. This one is specific to Firefox, while the others are mostly, again, engine. They are kind of happening in every engine. Global value numbering is an optimization where they try to kind of find duplicate operations. So it's a bit more generic than just the type check elimination. For example, if you're doing the same, if you're adding the same values twice, this pass will figure it out and not make you do it twice. And here were similar issues. Here, for this to happen, or for this to work correctly, they again needed to model correctly when side effects could happen, when things could change. This wasn't always correct. It's kind of hard, and it broke a few times. What's interesting here is that this can lead to different types of like fundamental memory in safeties. Because, for example, if you exploited this bug to remove a bounce check, you get an out of bounds write. If you exploited it to remove a type check, then you get a type confusion. It's kind of interesting to note, but yeah. Moving on, really for the temporal memory safety, I could only find one type of bug, which has to do with GC modeling and write barriers. Now, write barriers in JavaScript, they mean, or in garbage collected language, what it means is if your collector has scanned an object and then this object changes, then you need to tell the collector to rescan because it might now point to a new object. But then again, you can try to optimize this and figure out, well, if there couldn't have been a garbage collection triggered between here and here, then surely this object couldn't have been marked, and so on, and I don't need this barrier. And yeah, if you do your modeling wrong, then it again breaks this entire chain. Okay, here are two others. One is register allocation, pretty fundamental optimization, or maybe not even an optimization, I don't know, which broke, there's one bug that I could find, which is pretty nice also, but you could imagine this could lead to all kinds of issues if it goes wrong. Loop invariant code motion is the other. So there you see a simple example for that. The idea is you try to figure out if some operation really has to happen in a loop, and if it doesn't, well, you can move it in front and you save some executions at runtime. Those types of bugs, they were of the shape of this optimization moving, for example, an array access in front of the bounce check. That doesn't work. Or it would move an access to some object in front of the type check, right? And so again, this could give you different primitives. Maybe another interesting thing to note here is those bugs were specific to JavaScript core. That's the Safari engine. It seems V8, for example, never had these issues, and I think it's at least partially to do with how they represent the intermediate language. They couldn't really move an array access in front of a bounce check because there's some effect edge between those. But okay, so let's go a bit further in time. So back in 2017, 2018, I think a lot of people audited this or looked into this range analysis pass. I mean, at the end of the day, it's one file. You know that any bug in here gives you a nice exploitable bug, so I think lots of people looked at that. But then people started to move on. And the idea here is that, well, even if your range analysis is correct, but then if the actual machine code that's generated, if that is wrong, you still get a similar primitive because you have a difference between what range analysis thinks and what is actually the value at runtime. And so there were a number of bugs that would effectively just lead to wrong results being computed by a function, which by itself is not a security issue, but it becomes a security issue because it then breaks range analysis and it then breaks this entire chain. So for example, there were some what I just call pattern matching bugs last year. For example, there was one where they tried in the JIT, they tried to detect a rotation operation. So JavaScript doesn't have rotation, so what you have to do is some shifting and some bitwise operation. They try to detect, here's a bitwise operation and the input is a shift, so maybe that's a rotation. They would turn it into a rotation, but, okay, I guess it's going to come back soon. But it wasn't always a rotation, and so they ended up with wrong computations at runtime, and then this breaks this entire chain. Similar things, lowering, there was one bug where they just used the wrong machine code instruction, essentially, that didn't quite have the right semantics. Or there was one bug with common sub-expression elimination, leading to a very similar thing, a wrong result at runtime. And finally, a similar thing, as I would say, happened with these type inference bugs, where again, lots of people probably looked at these few files that did type inference, but then type inference relies to some degree on runtime state. So in many engines, there's some objects can say, well, my property here is a constant, or this property has a constant type, it's never going to change. Things like that. And so then, of course, if type inference sees that, it can be like, oh, okay, well, if the runtime says this will always have this type, then I don't need the type check. And then those were bugs that didn't even necessarily happen in the JIT. They could have been elsewhere in the engine, and some of them were, but they kind of corrupted this or violated those integrity guarantees. And then this in turn breaks the JIT, and it breaks this chain, and it goes to a type confusion. Cool, and there we have it. Again, the full picture. And yeah, there's lots of references linked here. So I want to talk very briefly about exploitation of these bugs. The main message here is just that these bugs are very powerful and they give you a great deal of control. So if you think of, for example, these type confusion bugs where you can remove a type check, this lets you choose the victim type, it lets you choose the target type, and it lets you choose the operation. Yeah, you can really build together your own type confusion bug, anything you want. And it's a similar thing for these spatial memory safety and temporal memory safety things where you can choose the array you are accessing out of bounds, the index, the size, and so on. So that really gives you properly nice exploitation primitives. Good. So fairly quickly, you might think now it's all JIT bugs these days. It's not. This is going back to the overview slides of the different components. There are bugs elsewhere, and this is just bugs from last year. So the JIT bugs, they were from up to 6 years ago. So this is just from last year, and you kind of see there's bugs everywhere. There's plenty of complexity in these other parts. But the thing is, many of these, they don't quite fit a good bug pattern. So many of these are one-off bugs. There was one garbage collection bug, for example, dealing with weak sets where they didn't scan in a certain situation. They wouldn't properly scan objects. There were interesting bugs in the runtime where they would leak internal values to script. There were kind of classic integer overflow bugs in the WASM compiler or other weirdnesses in the bytecode compiler. But yeah, again, lots of links here if you're interested in more details. And at this point, I want to hand over to Amy for exploitation and mitigations.
All right, so we just saw a bunch of different bug classes, mostly in the JIT. And we also saw how the JIT bugs have grown more complex, moving further away from the actual problem with like a out of bounds or whatever. We're getting really complicated into these complex interactions. But I want to talk a little bit about the other half of JavaScript exploitation in 2020, which is the exploitation. But before we can do that, we have to go back in time slightly. So let's look at what the average JavaScript exploit circa 2016 was. Now there's a couple of things here. So the bug that you would start with is usually something like an out of bounds, or maybe it is a type confusion, which you'll note is pretty much the same primitives that we still get today, as we just saw with all of our different JIT bugs. And then you would take that out of bounds or type confusion, and you would use it to either corrupt an existing JavaScript object in the heap, or you would try to create your own fake object in your memory and then inject that into the interpreter so then it tries to access it. And there were a lot of different techniques for this, but generally it was pretty easy to do for most bugs. From there, the next thing that you would see is trying to get an arbitrary read-write primitive. Now, this primitive was also very easy to do in the vast majority of cases, and it was usually done with what's called an array buffer. And array buffers are just a way for JavaScript to store some arbitrary memory somewhere. Maybe it wants to do some byte-wise computations. It needs a buffer to do that. So that's a great target for hijacking, because if we can corrupt where that buffer is pointing, well, that gives us a really easy primitive for arbitrary read-write. So that's what we'd usually see. And then you're probably thinking, okay, well, the next step of an exploit is, you get your ROP chain, you find all your gadgets. Don't even need that. In 2016, most of these engines still had read-write-execute JIT pages, which means all you had to do is get a function that was compiled, smash the code with your arbitrary read-write, and you're good to go. So honestly, pretty easy exploit chain. But now we're in 2022, so let's see if it's gotten any more difficult. Now, the first thing I want to talk about a little bit is how effective classical mitigations are. I'm sure a lot of you probably recognize these: ASLR, dep, stack cookies. But honestly, these are not very important when we're exploiting JavaScript, partly due to how powerful JavaScript is in the first place. The primitives that we get from the types of bugs that we're looking at usually give us a way to read memory either out of bounds or potentially confuse a pointer with like a floating point so that we can read it and leak that memory. So ASLR, most of the time, you do not need like a second bug or anything like that to bypass. Additionally, for dep or NX, where it's trying to prevent you from having your own executable shellcode, well, that doesn't really matter because we have a JIT. And regardless of being able to write the code into the JIT, we can also trick the JIT compiler into adding our code there anyway through various methods. So that doesn't really matter either. And then finally, stack cookies. Most of the bugs involve the heap. We very rarely see something that's just like a stack overflow. A lot of this stuff is logic bugs, so stack cookies don't really have any effect. But what about more modern mitigations? And when we're thinking about modern mitigations, we're usually thinking about control flow integrity or control flow enforcement. And this is going to give us a couple of different ways to prevent code from jumping to an unexpected area. So either to shellcode or to like a ROP chain. And there's a couple of different flavors here. So on newer ARM devices, we have pointer authentication, usually called PAC. And also, even more recently in the spec, we have branch target identification. These try to make it hard to call invalid pointers as well as making it hard to jump into code which should not be jumped into. On modern Intel chips, we've got shadow stack, which tries to protect return addresses, and we've also got our control flow enforcement tech, which is going to, again, try to prevent ROP. And on the software side of things, on Windows, for quite a while, we've had CFG, which is going to try to prevent, again, invalid jumps, but doesn't really do a whole lot for return addresses. So, okay, it's 2022. We've got modern hardware. You know, these should all be helping us out here. But when we actually go and look at the implementations and support within our JavaScript engines, it's mostly not there yet. The one that we kind of do see and will have to deal with is pointer authentication on our Safari devices. But V8 and Chromium, they're still working on having full implementation of a lot of these. Now, Chromium does support some of these pretty well, but the problem in a lot of these cases is the compiler. The JIT doesn't really have full support for these, which makes it fairly easy to bypass in a lot of cases when we're dealing with just the JavaScript engine itself. Now, of course, something like the sandbox might be a bit harder to deal with some of these, but we're focusing on JavaScript here. Okay, so I want to talk a little bit more about pointer authentication, since that is one of the bigger things that you may have to deal with if you're looking at Safari and you're trying to exploit an iOS device or some of the newer MacBooks which benefit from this. So if you're not familiar with it, the idea of pointer authentication is that you can cryptographically sign a pointer in such a way that when you use it, you can verify that the pointer has not been changed, or rather that the bits at the top of it match the bits at the bottom. And it does this through some hardware instructions which can use keys that can be loaded in various ways. So we've got the PAC instructions which do the actual signing, and the OT instructions which can verify. And then there's also instructions that let you do things like an atomic verify and branch or verify and return so that you avoid race conditions. And as an example here we have, this is a pointer to the JIT. We can see the PAC version, and we can see the upper bits are now set to our signature. Now, if I were to try to corrupt this and use it like we see on the side, when it actually goes through these instructions, the pointer is going to end up like this. It's going to have this high bit set, which will make it invalid, and so when you try to use it, you end up crashing. So this can be kind of tricky to deal with if you are trying to jump to your ROP chain or jump to shellcode at the end of an exploit. So let's think about some strategies of how we can get around this. Now, first off, I want to say, at this point, PAC's been around for a few years now, and bypasses, you could kind of consider them similar to bugs, right? If you have a bypass that's public, it's probably going to get patched pretty quickly by vendors. And also, if you're trying to work on this for your exploit, you might need to do some research, independently, try to find your own bypass, maintain it. But that's usually a one-time cost as long as you keep your bypass alive, since you can then reuse it for any other exploits. But just to give you an example of what some of these bypasses might look like, and these are really strict bypasses where you end up with a pointer, like an arbitrary pointer that you can sign, or a pointer that just jumps somewhere that it's not supposed to. One of the big ones is pointer forgery, and the idea of this is tricking the program into assigning an arbitrary pointer for you. And this is a bit easier when you have something like an arbitrary read-write, because, for example, all you have to do is look for writable memory that happens to get signed. So you can look for that control flow in your program and try to hit it. And there is at least one example of this in WebKit, and you can get some more information on the ref that's linked there. But this is what it looked like. So it was loading this POW function that then would be used by the JIT, so that if you're calling math.pow later on, and it would load this pointer from this writable page of memory, run our pack function and sign it. But of course, if we have arbitrary write, we can overwrite that pointer and have it sign something arbitrary instead and use that. Now, I do want to point out again, we're mostly talking about Safari here. Chrome and V8 are improving their pack support, but as I mentioned, JITted code is not currently supported, so that's a bit more of an easy bypass in terms of dealing with like a newer Android device that has pack. But this is maybe far and few between trying to find these kinds of things. So what else can we do? Well, we can kind of think about what we're doing right now, right? We're running JavaScript code, and we've kind of given it more permissions. We've given it the ability to read and write memory. So what if we can try to continue to give it different functionality without explicitly getting code execution? And this is partly something that you could do because there's a lot of functionality in the browser, which is kind of the functionality you might want for something like a sandbox escape. For example, certain syscalls, or doing IPC to the broker, or maybe other parts of the operating system. That already pretty much exists since it's needed to be used anyway. So what you might want to look for is things that you can call from JavaScript, usually through some bound API, like one of the many, many web APIs that exist, and then corrupt the data that that API then uses in some way to create a outcome which is favorable to you. So we kind of call this scripted code execution because you're not getting actual code execution. You're still in your JavaScript script, but you're calling and using these different functionalities that already exist without needing to corrupt these protected pointers. Now, a good example of this, which has mostly been mitigated recently, is Objective-C selectors. So what you could do is you could find these Objective-C calls that you could reach from normal JavaScript functions, and then give them corrupted Objective-C objects that set up this whole chain of library calls and do mostly what you want. And there's some good examples of this if you want to kind of see what that looked like. But that's an idea of what we're talking about here. Now, going from even here, what if you can't find the functionality you need? Well, you can potentially even think about other targets for a write. Now, we've got a lot of things going on in our browser. Not everything we can directly control from JavaScript. There's going to be a bunch of IPC stuff going on in the background, for example, that you can't directly call and say, do this IPC right now with this data. But the data for that IPC is still in your process, for example. So you could potentially use your arbitrary read-write to try to attack the integrity of that data that's going across the IPC, or also potentially try to get extra sensitive information to be leaked into your process so that you can then read it. So again, an example would be finding the buffer for the IPC, smashing the data as it goes out so that you're actually calling something different than what the original code expected. And again, you wouldn't need code execution to do this. But this can kind of cause a little bit of an issue, which is that you're creating new race conditions. You have your IPC thread or whatever you're targeting, which is going to be running and trying to send out all its messages. Meanwhile, your JavaScript thread is trying to get in there, write its malicious data, and hopefully not crash. And that can be kind of dangerous and unreliable if you don't necessarily know if your write is going to happen at the correct time. So you usually want to figure out a way to improve your reliability here, partly through something like exploiting a linked list. So one common, or one technique that we've seen to do this is if we find a linked list structure that is being used on some of these paths that we want to target, we can corrupt it with our arbitrary read-write to create this infinite loop. Then while that thread is chewing on the infinite loop, we've eliminated our race condition, we go in with our write, clean up everything, fix the linked list, and now it continues on its way without ever knowing that we were there. So this is just an exploitation trick to try to make these sort of races a bit more winnable. But maybe you don't care that much about escaping the sandbox, because to be honest, there's quite a bit of interesting data in the browser itself. What if we could get some of that data into our process so that we can then read it instead of trying to get out of the process and then reading it? So one way that we can kind of do this, at least in Safari, is we can use something like an iframe or different network requests to a different website. Now, normally, there's a thing called same origin policy, which tries to protect a website from accessing data from another site. So, attacker.com can't read your Gmail, for example. But if you were to load a site into an iframe, the process needs to actually be able to access that iframe to do things like sending messages. And in a lot of cases, it needs to figure things out, like, if you click somewhere on the screen, it has to get into that iframe and process everything that's happening. And so, historically, the easiest way to do that was to just put that data in the same process, so you don't have to worry about going between processes every time. But this creates a problem where now a compromised process can read that data, potentially inject scripts into that site, compromise the accounts that are logged in, potentially mess with persistent data, potentially even do something like install a service worker so that later on, when the site is accessed, you still have your JavaScript execution in that site. So this is actually pretty effective if you have sensitive data in the browser itself, which is one reason you may want to have things like cookies turned off or automatically log out of things fairly often. But anyway, this has been slightly mitigated in at least 2 browsers more recently. So both Chrome and I believe Firefox, in like one of the most recent major updates, or maybe it's on nightly right now, have implemented a thing called site isolation. And the idea of site isolation is that rather than having our iframe inside of the current process, it's actually going to be in a separate process reserved for that site. So we can no longer directly access that data, and instead we have to go through the IPC. So this kind of solves that problem. Now there's a few kind of edge cases there, like subdomains can be in the same process unless you turn on some better settings. But they kind of want those off because the more processes, the more memory usage, and Chrome already uses so much RAM anyway. So anyway, this is one thing that you can still do, at least in Safari. Okay. So at this point, we kind of get the idea that the first part of our exploitation is pretty easy still, but now it's maybe a little harder to get our end game. But there's multiple things that we can do. There's different strategies we can take depending on what our goal is in our exploit. So it's not really like game over yet. It's still fairly viable to complete this and go for like a sandbox escape. So maybe the vendors have started looking a little bit further up and trying to see, well, this arbitrary read-write is really powerful. Can they mitigate that to make it harder for an attacker to get that primitive in the first place? And one way that this has started being done is through pointer caging. The idea of this is that if pointers can be restricted to only go into certain regions of memory, then even if you have an arbitrary pointer, you can't really do a whole lot with it if all you can do is access a certain heap region. So the first real implementation of this is in JavaScript core, which is against Safari's JavaScript engine. They call it GigaCage. And it's essentially this large region of heap memory, which you can then tag any pointer. So you can see here there's this thing called caged pointer. You can put that type on any pointer you want, and it will force it to always point into this cage. And it essentially does that by masking off the upper bits and just adding it as an offset. So really, it just turns it into an offset into the heap rather than an actual pointer. And you can see the first thing that they really applied it to was the array buffer. As I mentioned before, a lot of older exploits, pretty much every time they use array buffer, so easy. So this makes array buffer less viable. But there's kind of a few, well, actually, first, so here's an example of what this looks like. It also has these runways on either side so that you can't just go out of bounds with like a very large length and a very large offset. That's guaranteed by 32-bit integer lengths. And then, of course, if you corrupt it, it's all going to force it into offsets into this cage. Additionally, they try to keep anything sensitive out of the cage, so it's mostly just data that doesn't really matter if it's corrupted, so it's like you can't really leverage that write into something more interesting. But there are a few issues with this implementation. One of them is that the devs themselves have to protect each of these pointers one at a time. They have to explicitly add that type to any pointer that they think is vulnerable. And then also, you have to guarantee that they're using the correct implementation of the uncaging everywhere. And this is a big problem for the JIT, where there's tons of optimizations, there's tons of different ways that these pointers can be accessed. So that's a lot of modification that has to be done to ensure that the caging is being done correctly. Additionally, there's just tons and tons of different pointers in the code. Even ignoring the DOM and other web APIs that get stuck in our heap, there's just tons of other objects we can use. So all an attacker needs to do is find a single pointer that is not protected, and they're pretty much good to go. And this is also can be made easier depending on what type of object you're looking at. Sometimes you can make a fake object that still has a vulnerable pointer in it, and it's pretty easy. So at least currently, the easiest method to do this is via the JS array. This is a very common data structure. It's used for almost all the different objects which are going to be in your normal scripts. So part of the issue, I think, that they haven't caged it yet is, again, the JIT. It's just very difficult for them to implement all of that in a way that is perfectly protected. So right now, you can take your butterfly, which is just the data pointer in our array. You can point it at something else, and as long as you have this non-zero value, which is the length, which it's going to check to make sure that you can access that memory, you'll be good to go. Now, this is slightly limited. There's also a little bit of an issue with certain bit patterns, but I'm not going to get into that. But generally, what you'll see is this is the initial read-write primitive, and then it's used to corrupt a more complex structure that has a better way to do a read-write to get pretty much unlimited arbitrary read-write. So GigaCage doesn't seem like the best right now. Maybe they could put a lot of effort into it, but when you think about what's really required, you're going to start finding that you need to make sure all the pointers in your heap are protected by a cage in some way. And part of the problem with this is there's a lot of external pointers that go to other things. Like I mentioned, the web APIs, the DOM, all kinds of metadata pointers. These would also have to be caged or removed from the heap. So if you were going and looking towards making this mitigation better, you'd probably want to first remove all of those pointers that don't point to the JavaScript heap, put them somewhere outside, and then give JavaScript a way to reference them. And this is pretty much what a future mitigation, which is being created by a Chrome team for V8 called Heap Sandbox. And this mitigation essentially makes it so that all of the objects in the JavaScript heap are going to be stuck within this 4 GB region. This is partly possible because V8 recently switched to 32-bit pointers to save memory. So that makes it a lot easier for them to just say, here's a 4 GB slice. Your pointers are 32-bit. You can't access anything outside of it. And then, of course, we have a table at the bottom, which includes the external pointers, as well as some type information to try to prevent you from specifying different indexes and causing a type confusion. So now, even if you have any of these out of bounds or type confusions that we saw earlier, you're going to kind of be stuck where your rights are only to other objects that you could have already corrupted or created. And what you're going to have to do is try to find other behavior somewhere in the browser, which you can kind of poke at through these handles or these indexes in the table. Which, when you think about it, that's kind of like what you do for a sandbox escape. Hence the name heap sandbox. It's trying to create another layer of security around the JS compiler. So this is kind of, I feel like, the way that we're going to be going towards in terms of securing these kinds of virtual machines, which have a lot of vulnerabilities in them. Again, it's not going to be bulletproof. There still can be tons of other issues in the web browser in all the different APIs, but it at least makes it a bit more difficult within JavaScript to corrupt other sensitive data. All right, so now we're kind of at our current state of most exploits. And again, this is a little weird because different browsers have different settings. Some have pack, some don't. Some have site isolation, some don't. Some have our heap isolation stuff. But generally, this is what we're going to see as all the browsers are catching up to each other. All right, so this is pretty much all that we have. But a few things just to reiterate. So we saw that there are fewer bug classes. They're more focused on the JIT recently. And outside of the JIT, there's only been a couple one-off bugs and parts of the code. Less vulnerability classes, but more complex bugs. Additionally, there isn't really much difference in the early stages of exploitation. It's pretty much the same as it's been for years. But the later stages are a little bit trickier in some cases, but not too bad. Future mitigations, though, are starting to look worse, as all these other CFI implementations come in, as they patch more bypasses. It is going to become harder and more of a concerted effort to actually bypass these things. But it's still not completely bulletproof. All right, so that's all we've got. Thank you very much. I guess if there's some questions, there's a microphone over here.